Yeah, I'll get started now. Before that, I first like to acknowledge the traditional owners of the land on which we are meeting, and I pay my respects to the elders past and present and the Aboriginal elders of other communities who may be here today. Good afternoon, everyone. Thank you for joining this month's webinar titled Mapping Air. I'm Sabrina Idris, a Centre for Safe Air Postdoctoral Research Fellow, and I'll be chairing today's webinar. As air pollution disperses across Australia, it affects the health of individuals and communities even across international borders. Mapping exposure to air pollution is vital for understanding who is most at risk, alerting communities to emerging threats, and targeting initiatives to reduce harm. This webinar will feature presentations from distinguished Professor Yumin Goh, Associate Professor Ivan Hannigan, Barbara Downs, and Abbie Brooke. Each speaker will present for up to 15 minutes, followed by a Q&A after all presentations have ended. So please drop your questions in the Q&A section. Our first speaker is Ivan Hannigan, who is an Associate Investigator of the Centre for Safe Air, Director of the WHO Collaborating Centre for Climate Change and Health Impact Assessment, and Associate Professor at Curtin University. Ivan is an environmental epidemiologist and uses extensive experience across a wide range of environmental health issues to focus on climate change and health issues such as droughts, fires, dust storms, and heat waves. His research focuses on data analysis that disentangles health effects of environmental changes from social factors. Over to you, Ivan. Could you please share your screen?
Thanks, Sabrina. Welcome, everybody. And I'd like to acknowledge the lands that I'm on. Traditional owners are the Whadjuk people, and I pay my respects to elders past, present, and future. So my topic's spatiotemporal air quality modelling, which is a very rich history through quantitative geography and atmospheric chemistry. And there's a lot of developments that have happened in the last few years. But I thought and Sabrina explained that this is pitched at a very general researcher community. And so I thought I'd start with the simple and general and then move through to the advanced. So as we go through, you can see the list here. The basic foundations were developed called kriging, which is geostatistical, and then goes through more advanced statistical methods using regression and generalized linear modeling, which add covariates and predictors. And then we can move beyond GLMs to generalized additive models, which capture nonlinearities really well. And as I said, there's an atmospheric chemistry arm to this area as well. So that's called chemical transport modeling and dispersion, which is based on physics. And then there's really interesting ways that you can add on to the underlying models using residual kriging. I'll explain about that. And they get into some of the ways that we can include time and space at the combined. And then the modern movement into machine learning, sometimes called AI, which we've been developing new methods in ensembles, deep layers of these things, and finally finishing with something that we've implemented recently called Bayesian maximum entropy blending, which puts predictions and observations together to optimize that. So essentially the basic problem is that we measure the environment at points in space, and then we need to be able to predict using a whole range of information what would be happening in between those points of observations. So that model on the left is a simple kriging model, and you can see it's very general. It shows you that air pollution gradient over the city is highest in the middle. But then on the right, we've got the output from a complicated Bayesian model, which shows more information. And that's what we're hoping to get. But going back to the foundations, this kriging model basically looks at the relationship between points. So you can see that the x-axis is the distance. So between any observation, you can look at their relationship using semi-variance. And so this variogram can be computed and then used to model the predictions across space. This is then further enhanced by normalizing the data. And so this Kriging family of methods, ordinary, simple, and universal, have been developed, and they're very robust. They basically use the correlation between observations in space, and you can see that this is a set of points on the x-axis. There's also a y-axis for x and y coordinates, and this can then be used to interpolate the trend across space. That's improved by using predictors in a linear regression framework. And so this is a fantastic choice of colors by my colleague Haresh. It's a little bit hard on the eyes if you look at it for too long. But essentially what it's saying is that in the neighborhoods of each observation point, which is the dots, you can go out in these circles of buffers and get the information about what's happening in terms of GIS data, sometimes the land use, sometimes the weather, sometimes satellite images. And we can have these ground-based sensors and these also sensors in the air. And we can put together a huge number of these predictors, GIS, satellite, weather, and land use predictors. Here's a list of the ones that we've been using and putting together in our CARDAT data platform to be used in that kind of method. However, there are major issues in that approach that have been spurred us on to go further. This is sometimes called LUR. I just want to make sure that if you've heard that term, you know that this is what we're talking about, but essentially it's actually spatial linear regression. This can get confusing with terminology when you then try to compare what's been happening in LUR papers to general regression methods. I want to point out that traditionally that approach avoids nonlinear terms and complex interactions and has a really problematic focus on forward stepwise variable selection, which, as Professor Frank Harrell, the famous biostatistician, has said, if it was invented today, it likely wouldn't pass peer review in a statistics journal. So what is better is actually these more complex modeling frameworks. Generalized additive models capture nonlinearity really well. And so this is an example from the famous American NMAPS and Medicare air pollution study, just showing you that when you put these multiple variables together in a GAM, you can get these lovely nonlinear and more complicated model structures. GAMs also use splines. And so as you can see here, this is a spatial model at each time point. And so we're starting to bring in time here. And I'm just modeling the latitude and longitude. So it's capturing the spatial autocorrelation and stepping through the time period for this variable. As you can see, the bottom graph is at a single point, the airport, and the blue line is the prediction from the spatial model at each time point. Now, if we add the time dimension in that same model, you can see now the model structure is a spline on latitude, longitude, and time. The blue line is now very smoothly connecting the data across time as well. And you can see the animation has now smoothed out that kind of jagged, jumpy mapping that was happening before. And this is very powerful to capture variables that are changing over time, not just in space. And so we leverage off. However, in this particular example, I'm showing that you actually need to be fairly careful about tuning that because it's over smoothed in time in this example. And so the blue line is actually fitting quite poorly, but it is leveraging across that time trend. Now, this is a spatial version where we can then explore that error between the model and the observations. In this hybrid between a regression model and a Kriging model, it's called residual Kriging or regression Kriging. And basically, you can see that you've got samples at the circles, and those are the observations. And then you've got a jagged line, which is the actual distribution that we're trying to predict and get from those points. And then we've got a smooth dashed line, which is the result from our regression model. And what we can do is then get a model of the residuals, which are the the difference between our prediction and our observation, and then add that back on to further enhance. So you can see the final result is the thick grey line, and that's better fit to the actual reality than was achieved by the regression model without the follow-up using spatial autocorrelation in the residuals. Now I want to go sideways. So we've been talking about statistical approaches thus far. There's an entirely kind of parallel universe in physics and atmospheric chemistry that has built up over decades, understanding from the basic physical and chemical and meteorological knowledge. And so this is a diagram showing what a CTM does and disperses these variables around a three-dimensional space over time. And a different approach that's in that same family is the trajectory modeling approach. You might have heard of back trajectory, or these are examples of forward trajectory models. And they basically say that that dispersion of that particular pollutant would probably go in these directions. Now, moving back to statistical approaches, and well, it's kind of, we're getting to a point where statistics and the physics and chemistry are coming together, and they're just different types of model, and we can put models together. So in this next section of my talk, I'm going to talk about multi-model approaches. And so to do that, I'm going to start with these machine learning models. And this is a random forest that puts together a big number of tree-based models, which are that you can see each one of these, that is a little cluster of lines, circles, and squares, is a decision tree model for classification. It also works with regression on continuous. And they all get put together into a final modeled estimate. This has been developed over time. We've got random forests, as I just showed. Then the generalized boosted machine also uses trees, but uses a different way of growing them and using the residuals of those trees against the observations. And extreme gradient boosting, which also extends even further, and leverages a huge number of computer science techniques, which make it fit faster. Putting those together, multiple models, and not only statistical models, but chemical transport models together into an ensemble has been shown to improve things even further. And so this was demonstrated in this 2019 paper that used a large number of model predictions and then got a couple of ensemble aggregations of them. The first one was just a simple median of all of their predictions. It's pretty nice. And then they also tried a weighted average, where they used kind of a measure of how well each model did against the validation sites as weights. And then that was considered the best. Moving on yet again, now we have the deep ensemble machine learning approach that Ming and his team were pioneering, and we implemented this recently in Ozone and published. And Ming's team have done it with PM 2.5 very effectively. And basically, you've got those basic learners. These are all tree-based learners, RF, XGBoost, random forest. And they give you a set of predictions, but then you can use those predictions as predictors. And so you model them again in this meta-learner phase, and finally putting together a weighted prediction at the end. Finally, we get to the Bayesian maximum entropy data fusion approach, which is supposed to optimize all of these inputs using Bayesian theory and give you a posterior probability, which collapses all of that information into something manageable. And we first implemented this in 2017 in NO2 in Sydney. You can see that we've got the observations in the triangles and stars, a CTM in the bottom, a regression model in the top right, and we put it together and demonstrated that it works really well. It does this so in the same point location, we've got Liverpool, New South Wales observed, and then a range of different modelled estimates with their errors. And so you can see that some of these are closer to the observed than others. And you can put them all together in a Bayesian framework using this entropy index. And that's just an explanation with using children's toys and the prior knowledge that if you knew that there was 2 blue balls in a certain place, the best guess is that probably the rest of the toys are spread out. You're quite uncertain, and you can estimate that uncertainty. Now, this is where we've gotten to in 2025. The latest implementation of this was the paper published earlier this year, Deep Ensemble Machine Learning with Bayesian Blending, improved the accuracy and precision of modelled ground level ozone for New South Wales in Australia over the time, sort of a spatio-temporal model. And as you can see, we did report that we did get these improvements. We did improve precision and accuracy. However, it came with a very large cost of complexity and computational demand. And so I wanted to finish with the conclusion that actually the best modelling approach depends not just on predictive performance, but also the research context, the data availability, and the research constraints that are in the team doing the work. Because some of these projects are epidemiological. They will benefit most from the improved precision and accuracy and really getting an understanding of what's going on. But then in policy scenarios, informing what-if scenarios may have a totally different set of criteria. Then we have regulation and monitoring and evaluation of the legislated variables and indicators. And then we have planning, land use zoning and development applications. So all of those applications deserve a different set of decisions. So I'll finish there and just acknowledge all of the partners and stakeholders who have made this work possible. Thank you.
Thank you so much, Ivan, for sharing your knowledge on spatio-temporal air quality modeling. There are no questions yet in the chat, so please drop your questions in the Q&A section. Our next speaker is Yuming Guo, who is a Chief Investigator of the Centre for Safe Air, a distinguished Professor of Global Environmental Health and Biostatistics, and Head of the Monash Climate Air Quality Research Unit. His research group focuses on environmental epidemiology, biostatistics, global environmental change, air pollution, climate change, urban design, residential environment, remote sensing modeling, and infectious disease modeling. Over to you, Yumi.
Thank you, Sabrina. I'm trying to share my screen. Okay, can you see it?
Not yet. Yeah, now we can see it.
Okay, great. Okay, thank you very much, Sabrina, and hi everyone. Very nice to meet you here to give a talk. So I would like to acknowledge the traditional owners of the land on which we meet today, and I would also like to pay my respects to elders past, present, and future. For my presentation today, we will look at the mapping global air pollution and its mortality burden. I'm declaring there is no conflict of interest for this presentation. Okay, so why we want to map air pollution and its mortality burden or health burden? Because there are several reasons. The first one, we can understand the spatial and temporal patterns of the air pollution and the mortality risk and mortality burden. And the second one, that is, the mapping air pollution and the mortality burden can inform public health and the exposure assessment, and also it can guide policy and regulatory actions. And also this work can support environmental justice. We can understand which area are more sensitive or more vulnerable, and then we can provide some specific or precision intervention. And we can track the changes and evaluate the intervention if we take some policy or actions to reduce air pollution or reduce the air pollution related health outcomes. And also we can improve the public awareness and engagement to make this area going forward. Of course, there are many challenges in this area. The first one, which is the there are very few monitoring stations of air pollution across the world at this moment. For example, in Australia, we just have maybe just less than 200 monitoring stations for air pollution. And if we go beyond to the worldwide, we have tried our best to get the available data set for the air pollution monitoring. In fact, there are just maybe more than 10,000 stations, air pollution monitoring stations. That is quite few. For example, specifically for Africa, we can say there are very, very few air pollution monitors. So we don't have air pollution data. So this means, if we wanted to make some policy, or if we want to understand the impact of the policy, the air pollution on human health, we don't have the data in this area. So we should try our best to do something to get the air pollution data, to estimate air pollution data. And as Abbie said, there have been so many pollution modeling methodology, from the very basic linear regression to the recently developed AI models. So, of course, each methodology has its advantage, and also they have some disadvantage. We should combine some of them to improve the model and to improve this field. So for our group here, currently we are doing some work to estimate air pollution across the world. So which model we are using? As Ivan said, we have developed a mixed ensemble machine learning, or deeper ensemble machine learning. Using this machine learning data, this methodology, and then we can combine the ground-based PM25 or air pollution monitoring stations data. Like we get the more than 100,000 more than 10,000 stations data, and combine them with the satellite remote sensing data, and also the meteorology, like temperature, humidity, wind speed, rainfall, air pressure, and sunshine duration. And also we also need to combine with the land using information, like land cover, vegetation, and road types, and some other predictors like elevation, fire density, population density. We put all of them together to predict the air pollution at daily level, monthly level, or annual level. Now, another type of the data, that is chemical transport model output, because this output can give us some information for the proportion of the each sources, like wildfire related or industrial related, or some other, or agriculture related. So if we get this data, so we can divide the total air pollution into different sources. Okay, so this is what we are doing. This is the model performing for this global air pollution air pollution estimation model using the deep ensemble machine learning. The left one, that is the daily exposure, and the middle one, that is monthly exposure, and the right one, that is annual exposure. So we can say this model gives very good prediction. For example, for the daily exposure, the R square is 0.9. That means 90% of the observed air pollution can be predicted or interpreted by the predicted PM5. And for the monthly R square, that is 0.96, and then the annual, that is R square 0.998. This means the estimated air pollution is quite similar to the observed, and the estimation has a very small RMSE, which is indicating the error. Actually, the error is very small. So that means the estimated air pollution can be used to do the health risk assessment or health burden assessment. Okay, so this is the estimated PM5 from this model between 2000 to 2019, and this is daily level. Because we have the daily level data, so we can do the average into weekly, monthly, seasonality, and also annual. In general, this map is showing the annual average of PM5 from 2000 to 2019, and we can get the trend. For example, for the right bottom map, that is the change in the annual mean PM5 from 2000 to 2019. So we can say in some areas has an increased trend for the annual PM5 level, particularly in the East China and the North India and Russia, and some parts of of Australia and also Canada. And also we found in 2019 only 0.2% of the global land area and 0.001% of the global population had an annual exposure to PM 2.5 as concentrations lower than 5 microgram per cubic meter, which is the guidelines from WHO. This means, most of the areas or population have been affected by pollution by PM5, and more than 70% of the days have been daily PM5 concentration higher than 15 microgram per cubic meter. And this is WHO guidelines. So we can say many people are affected by daily PM5. Okay, this is the trend for these different continents. So look. So on the bottom, that is we can say this is a trend from 2000 to 2019 in Australia and New Zealand. We can say for Australia there is an increasing trend, and for Australia there is also increasing trend for the PM5. That means Australia and also New Zealand, even we have very good air quality in general, but the trend is a little bit serious than other countries or regions. Okay, because as I said, we can divide the estimated air pollution data into different sources. So we can get the wildfire related PM5 from 2000 to 2019 using that model. So the right map that is showing the annual average wildfire PM5 in 2019, and the bottom that is the trend from 2000 to 2019. And for the top map, we can say many areas of the world have been affected by wildfire related PM5 in 2019. For example, the serious regions might be the Southeast Asia and Northwest Australia and Southeast Australia, and also Russia and the south part of Africa and South America, and some part of Canada and the West US. And also, if we look at the trend of the wildfire PM5 from 2000 to 2019 for the bottom map, we can see many parts have an increasing trend. For example, the Southeast Asia and Russia, south part of Africa, and then most part of South Africa and Canada and the West US, they have been affected or increased in trend. Okay, this is the trend for different continent or different region. For this panel, for the F, that is the trend for Australia and New Zealand, Australia. So we can say in general, the trend is not changed too much. It's just similar, but if we look at just 2019, we can see there is a sudden increase. That is because there was a very large wildfire in 2019 and 2020. But if we look at the panel E, that is for the North America, we can see there is an increasing trend for the wildfire related PM5 and ozone. For the blue one, that is ozone. For the red one, red color, that is wildfire related PM5. And also, if we look at the bottom right, we can see we have the seasonality trend. In general, for Australia, Australia, New Zealand, in December, January, there has a higher concentration of wildfire related PM5 and ozone than June and July. Okay, so after we got the air pollution data, of course, we can perform some health risk assessment to understand what is the impact of the air pollution on human health, and we can map the burden across the world. So currently, we have collected, we have developed a multi-country collaborative network that at this moment, we have for the membership countries, more than 60 countries, and we have collected mortality, morbidity, and birth outcomes from more than 3,000 communities. And also we have the weather conditions and also the estimated air pollution data. So if we combine all of them together, we can perform the risk assessment and the burden assessment. Okay, so this is one of the output from the global mortality burden due to daily PM5 with our. So why we want to do this one? This is because if you are very familiar with the GBD study, they have estimated the annual average air pollution and the annual burden for the mortality. Actually, they just look at the long-term effect. They ignore the short-term effect, the daily variation air pollution, the daily variation of mortality. Actually, there are two different concepts and two different types of the disease burden. So we need to make some calculation. So based on our multi-country collaborative network mortality data and also our estimated daily PM5 data. So we get the relationship first, and then we calculated the mortality burden, daily mortality burden due to daily exposure of PM5. So in general, across the world, about 1 million deaths can be attributable to daily PM5 exposure. Okay, the short-term effect. And then if we divide them into different regions, we can say in general, Asia has a higher mortality burden than other regions. And Australia, including Australia, we can say Australia, New Zealand. Each year, there are about 600 deaths can be attributable to short-term effect of daily exposure to PM5. And also we can look at the map at the left. So East China and India, North India, highly impacted by the daily exposure short-term effect. And so we can say that means if we add this value to the GBD study, we underestimate 1 million deaths from daily PM5 exposure short-term effect. This is just the daily PM5. If we also consider about AO2, SO2, ozone, that means the burden might be much higher than 2 million or 3 million. Okay, so that means the GBD study has underestimated the impact. Okay, and this one is looking at the trend from 2000 to 2019 at different continent. For the A, that is the annual deaths attributable to short-term PM5 exposure, and the B, that is death attribution, death fraction attributable to short-term PM5 exposure. C, that is annual deaths for 100,000 population attributable to short-term PM5 exposure. And for the blue color, that is for Australia, including New Zealand and Australia. So we can see, in general, the trend is flat, but from 2017 to 2019, there is a little bit increase in trend. It might be because of the increased air pollution in the 2019 and 2020. Okay, and also we can look at the average annual mortality burden attributable short-term PM5 exposure in urban areas in 2000 to 2019 by different continental regions and sub-regions. Here is the Australia and Australia, New Zealand, and others. So we can see in general, the death fraction in these regions in Australia, and New Zealand, a little bit lower than other regions. And this is the death per 100,000 residents in urban areas. So we can say, comparing with other regions or continents, Australia and New Zealand and Australia has a lower fraction, a lower rate than other regions. Okay. And also we calculated, perform assessment for the mortality burden related to wildfire smoke at global level. So why we do this one? Because recently the wildfires happening very frequently and more and more serious, but the mortality burden due to wildfire smoke is still limited. And also many studies only look at the daily variation, for wildfire PM5 and wildfire and mortality and daily mortality. They have ignored the long-term effect of the wildfire smoke. So in this study, we combine the long-term effect of the wildfire smoke and the short-term effect of wildfire smoke together. For the wildfire smoke, well, we consider PM5 and ozone both of them. So we can say for the for this map that is showing the annual average attributable mortality rate attributable to fire-related air pollution, including PM5 and ozone, and the corresponding trend for the 2000 countries from 2000 to 2019. So in general, many countries have been affected by the wildfire smoke, and particularly in Russia, south part of Africa, South America are more affected, and Southeast Asia are more affected. So for the right panel, that is looking at the trend of the annual attributable deaths and attributable mortality rate to the landscape fire source air pollution from 2000 to 2019. So in general, in some parts there is an increased trend, but in some part there is a decreased trend. So that means, different regions have different pattern. If we want to develop some policy, we need to consider the region specific or country specific. Okay, here is give a summary for the estimated wildfire related wildfire smoke related mortality burden. So at global level, annually there was about 1.5 million deaths can be attributable to wildfire smoke for PM5 and ozone. And for the cardiovascular deaths, that is about 500,000. For the respiratory, that is 0.2 million. Of course, if we look at where is Australia, that is New Zealand, Australia, we can see annually there was about 3,800 deaths can be attributable to wildfire smoke. And for the cardiovascular, that is 1,500. For the respiratory disease, that is 400. Okay. Of course, there are still some directions in this field. We still need to do a lot of work to improve the air pollution prediction and the mortality burden prediction. For example, we should integrate the multi-source data. The data is more and more currently. There are many resources. We should combine them. And the second one, we can advance or we can use the advanced methodology like machine learning or AI. Currently, maybe if you have been aware, there is a new paper just published by Nature. That is a group of Google researchers. They just developed a foundation model to predict air pollution at global level. And that model is quite well. So maybe in the future, we can incorporate our method to their foundation model to do some real-time prediction of air pollution. And the third one, that is high resolution real-time prediction. This is very important. If we can develop a model to perform the real-time prediction and the high resolution prediction, it can be used for the behavior planning or something or action. And also the personalized exposure forecasting is very important. Currently, we just can estimate the area level, community level air pollution, but it is still very hard for the individual level of exposure. So, but in the future, if we can incorporate something like some very cheap, low-cost sensors for personal usage, that should be very helpful. And also the open, transparent, and equitable tools can be developed in this field, like the Google team. Their platform currently they want to be open. That is great achievement and very helpful for the community. And also for the health link forecast system is also very important. If we just look at the air pollution exposure, air pollution prediction, then we might miss something because different populations have different health risk from the air pollution. If we can give some precision health linked system, that should be very helpful for each person or each individual. Okay, thank you very much. Happy to discuss.
Thank you so much, Yuming, for sharing your excellent work. So our last two speakers are Barbara Downs and Abbie Brooke, who are Senior Program Officers at Brisbane City Council. Barbara is an environmental scientist also with a background in healthcare. She has 24 years experience in local government working in air quality policy and management. Barbara gets involved in all kinds of air-related topics to protect the health and well-being of people in a densifying urban environment, from city planning to smoke complaints and everything in between. On the other hand, Abbie Brooke is an environmental engineer with 15 years experience in local government, specializing in air quality policy and evaluation of air quality impacts from developments. Her focus has been on understanding pollution impacts and using planning tools to prevent future harm for residential development close to industry and roads in a constrained city environment. She has an extensive background in air quality consulting and engineering research. Over to you, Barbara and Abbie.
Thank you. Well, this will be a little bit more local to Australia, not the global data that we've been seeing. So Barbara and myself will be presenting on the use of mapping tools to look at protecting air quality in Brisbane. So a brief introduction to Brisbane and what we do for planning. So we are a local government with the largest population in Australia. We've got greater than Tasmanian population and we're still rapidly growing. So we use the City Plan 2014 to look at governing our approvals for new developments or material change of use. And in the context of our pollution impacts, we've developed mapping tools that focus on that interface between the pollution sources and the sensitive uses in our city. So in circumstances where we're talking about the residential encroachment on established industries, we'll be looking at the industrial amenity overlay, which is the context that I'll be talking about. And where we're looking at residential developments near roads, we'll be looking at the transport air quality corridor overlay, which is what Barb will be referring to. So this is a bit of a lesson in why we're doing what we're doing. Ideally, we want industry to be well separated from sensitive uses, where there's maybe a kilometre or two distance from a large industry. But the reality is quite different. So in reality, a city like Brisbane has a lot of development over time. On the left-hand side of that photo are some tall stacks, the high impact industry that's emitting some pollution into the neighbourhood, and the existing residential areas that are only, I guess, tens of metres away from, or maybe hundreds of metres away from the stacks. At the moment, they're low-level residential dwellings, but there's a potential for multi-unit dwellings and high-rise towers in that region, and there's a push for that from our growing accommodation needs. So that really highlights the context of how we're trying to manage our air quality constraints. And in this presentation, where I talk about sensitive uses or sensitive zones, it's referring to residential dwellings, it's referring to childcare centres, schools, hospitals, and also residential aged care. So focusing on those uses where people are spending a lot of time. And what does the overlay achieve? So I've talked about the idea of it. What we're intending to do is to manage that encroachment of a new residential development on an existing industry, protecting the health of those new residents that aren't there yet, and also to ensure that we still have viable existing industrial operations so that we're not crowding them out and forcing them to close prematurely just because they've got complaints from people living nearby. The overlay itself is a screening method to look at the potential for air quality impacts. So it's not the end result, it's a tool and a stepping stone in the process. We're looking at protecting future residences that aren't there yet. So we can't use any tools like complaint data to see if there really is an impact from those existing industrial uses. The use of an overlay helps us to reduce the need for upfront specialist studies, and it gives the developers of these residential, well, generally residential uses or sensitive uses, gives them transparency about the potential constraints on a site. So they can do that due diligence before they commit to purchasing the location, to make sure that there will be an opportunity to develop the scope of site that they want to. So on a citywide basis, this is the Brisbane city area. So we're a bayside community. We've got the large Brisbane River running through the centre, and we have multiple industrial zones or areas located through the city. So quite a lot at the Port of Brisbane area, and some larger industrial areas in the north and south of the city. So the overlay reflects generally that pattern of industrial development over time, and then some smaller overlays in that purple hatching that reflect those individual industries where we've got kind of an outlier to the system. Zooming up on that overlay, we have industrial zoning in the purple to the bottom of the map there. So the industry is clustered together. I can't remember this exact location, but it's probably been there for a long time. And we stagger the intensity of the industry. So new developments are the less intensive, low impact industry developments can go closer to housing, and the more intensive the use, so it's a medium impact or a high impact industry use, will need to be located further and further away from those sensitive uses, just to help manage the future impacts. So here we have the pink zoning, the pink and light pink and dark pink, that are the residential zones to the top, and the purple hatching, which is kind of a bubble mirroring some of that industrial zoning, actually comes from individual sites within those industry zones that are located too close to the residential areas to be considered okay through historical land use. And so this is what the overlay actually does. It's this trigger for your lot. When you do your development, you're buying a certain parcel of land, and this gives you the trigger to see whether you're going to need to do more investigation on the actual impacts of the industry on your block of land. Just a bit of background about how we developed the overlay. So we did do air quality modelling. We took some typical industries that we have in Brisbane. We looked at the size of the industry and the typical controls that we will get. We know that there will always be residual air emissions from industries. Even the best bag filter will still release some particulates into the air. So it's allowing the distance to try and build that distance into our planning so that those impacts can be managed. Through our modelling, we determined what industries go into each of the low, medium and high impact industry zones. And that's based on allowing either industry adjacent to residential developments in the low impact industry case. The medium impact industry allows for a 250 metre separation, and the high impact industry needs at least a 500 metre separation. There's also a more extreme one as well. It's a special industry. So the overlays are for the existing industries where they're too close to sensitive zones and we need to protect that encroachment. It's a trigger then for the site-specific air quality assessment that will be used for gaining a development approval. And during that more site-specific process, you would need to look at the applicable air quality planning criteria to see what's an acceptable level of impact, and the air quality assessment methodology that are laid out in the city plan document. And we also use those land use zoning, the low, medium and high impact industry zones, and the location of sensitive zones to prevent future encroachment. So it's a way of managing the difference between the sensitive uses and the polluting uses. So I'll hand over now to Barbara, who's going to talk about the development cluster roads. Thank you.
Thanks, Abbie. Hi, everyone. So I'll be talking about the Transport Air Quality Corridor Overlay, which addresses development close to major roads. And we needed to do this because there's a lot of pressure for increased housing, even on major roads. We also have a policy at Brisbane to try to encourage increased density of housing near public transport hubs and amenity in an attempt to reduce that car dependency. But a lot of those places are also close to busy roads. So we needed to understand a little bit more about the impacts of that. And we did some air quality modelling to try to estimate what that exposure is close to those busy roads. So the characteristics that you have to put into your model included some of these things here. So what's the traffic volume on your road? How congested does it get? What's the proportion of heavy vehicle use? Because that's important because they're usually diesel, and diesel particulate emissions are even more damaging to health. And road gradient is the other aspect that's quite important to include, because if you consider a heavy truck going up a steep incline, that engine is under heavy load and it emits a lot more pollution out of the exhaust in that situation. So we looked at all of those factors, put it into the model, and the model then comes out with some pollution concentration levels estimated at different distances from the curb. The other bit of research we did was a literature review into street canyons. So you might be familiar with these. We're talking about tall buildings either side of a road, and they trap the pollutants into that space close to the road, close to ground level. The pollution recirculates and builds up and it can't escape. So we need a built form that allows the pollution to escape and disperse away. That's quite an important factor. Oh yes, please, Abbie. Who's changing my slides for me? Thanks. So we found, as have lots of other people, that pollution concentration drops as you get further away from the curb. The first 20 metres, quite dramatically so. So that's most importantly. And we looked at all the different concentration levels that we got at different distances for the road and tried to create categories of road based on that, and tried to think, well, what distance from the curb is an acceptable distance where our pollution levels might meet the air quality guidelines that we hope for. So we've got categories of road, different distances, new sensitive uses, that is like a new apartment block has to comply with whatever that separation distance is according to the category of road that you're on. Thanks, Abbie. So it might be a little bit clearer when we see the map. And that's a little section of inner city Brisbane right there. The pale pink shading shows those roads that we want to consider a separation distance. The coloured line down the middle of the road tells you what category you are, 1 through to 10, 10 being the worst. So, for example, you're that dark green category 2. If you want to put a new block of units there, you might need to be 15 metres back from the curb, according to our city plan. All the intersections are also marked and they have their own separation distance as well. The darker pink shading, that relates to roads where we want new developers to consider their built form in such a way that they're not creating a street canyon effect. Thanks, Abbie. And that's what it looks like across town, all the major roads and intersections across Brisbane. Thank you. And that's what it looks like in the city plan, trying to give a visual representation there. So let's say you're a category 1 road and city plan tells you you need to be separated 10 metres back from the curb. But our study also showed us that in the vertical direction, pollution disperses more quickly. So whilst you might need to be 10 metres back in the horizontal plane, you might only need to be 5 metres up vertically. And that is quite handy for the podium design, which is very popular in the inner city, where you might have a commercial use on the lower floor, like a shop or a restaurant or something. that can be that little bit closer to the curb because it's not a sensitive use, right? You're not there 24/7, so that can come a bit closer, whereas the sensitive use, the residential use, could go above that podium or set back a little bit, and it achieves a good separation from the road and from that pollution source. Thanks, Abbie. Childcare centres, we've made them a special case because recognising they're a higher risk, they need a site-specific air quality assessment. The overlay we were just talking about, that's a generic tool, which is a little bit conservative. It doesn't take into account the actual site-specific characteristics, whereas childcare centre, we do want you to do that. We want you to look at the exact topography and road configuration, built form, everything around you. Consider that, do your air quality assessment, and you get a much more accurate idea of the impact of that site. Thanks. And the street canyon effect, so the picture on the left, it's pretty obvious there. You've got long row of tall buildings over a narrow road. The pollution is trapped. It builds up there to dangerous levels close to ground level. That's what we want to avoid. And on the right, that's what we're trying to encourage in city plans. So we want to have gaps between buildings, gaps between towers, variation of facade and roof line that shows that increases the air turbulence in the area. And that helps aid the dispersion of pollution up and away from the road. Thanks, Abbie. So just to summarise, overlays, they have their limitations. They are generic. Like I was saying, you can't take into account all of the site-specific characteristics of every lot. And they can be difficult to update because, of course, industry changes, the traffic situation changes, the fleet changes. We might get more electric vehicles, for example, or more trucks, for example. So you can't really deal with that until you do your next big overlay update. But we think it's been a very useful tool, and it strikes a balance between a pragmatic solution to allowing development versus making everyone do costly air quality investigations that would just be too onerous and inappropriate. It also is a visual flag, so that tells people where those pollution risk areas are, developers as well as our own planning teams. And it tries to avoid those complaints that would be unresolvable once the building's built. There's no going back from that. You end up with a situation that you can't resolve. And hopefully, if we get it right, we're helping to reduce the health burden on our community. So that was just a very, very brief overview of both of those overlays. There's a lot more detail behind them. So if anyone's interested in the details, Abbie and I would be only too happy to chat another time if you'd like to drop us a line. Thank you very much for listening. Thanks, Sabrina.
Thank you so much, Barbara and Abbie, for sharing your fascinating air quality mapping exercise. Now we'll open the floor for any questions that the attendees may have. We only have 2 minutes left, so we'll try to go through this quickly, but if we don't have time to go through all the questions, then we'll respond to them via email. There's a question from David about what are the plans for rolling out a more extensive monitoring station network in Australia? Yuming or Ivan, do you have any thoughts about this question?
Yeah, I think this question should be related to the government, not for us. So in general, to install the more air quality monitors, let's develop, related to the urban design and the EPA. But for us, for researchers, of course, maybe we can develop some low cost sensors. Or for example, we also develop a new technology to translate or transfer or convert the current traffic cameras to the air quality monitors. So maybe we can use this technology to develop more air quality monitors in the future. And also we can collaborate with Abbie and Barbara in Brisbane to do some work in this field.
Thank you, Yu-Ming.
Can I add,
Um,
Sabrina,
yeah.
that's really important, that the work that the government does. It's the gases and particles that they focus on. Not many people consider biological air pollutants, but there's pollen and fungus, and none of the government legislation is focused on them. So the research community has major contributions in expanding the monitoring of those. There's a university-led network of pollen monitors around the country that has recently expanded. So I haven't heard any substantial plans from the government side, but the research community is expanding our research-focused monitoring.
Thank you, Ivan. And Barbara and Abbie, there's a question from Stephen. He's asking about what about balconies and direction they face? Do you have any thoughts about this?
Oh, yeah, that's a good question, Stephen. Balconies, we haven't got any requirements for which way balconies face, but there are other people in the planning teams who like to see balconies facing the road. And we don't like that too much. It's purely a visual thing, I think, to have a nice looking streetscape and to give people the opportunity, I guess, to open their balcony, which some of these roads might be less busy late at night, so I guess, once the traffic has died down a bit, you might have the opportunity to open up your balcony, but we don't have any requirements for that at the moment.
They would be considered as part of the sensitive use, though, so they would be included in that spatial orientation of what's sensitive.
Thanks, Barbara and Abbie. So it's already 1 p.m. So I'll just conclude today's webinar. We'll get through the rest of the questions via email. So as we conclude today's webinar, I want to extend my sincere appreciation to Ivan, Yu-Ming, Barbara, and Abbie for their excellent presentations on this topic. We hope the attendees have found the information valuable and insightful. Again, we're very sorry that we did not manage to get through all the questions, but we'll pass them on to the speakers and be in touch with you soon. If you have any further questions or would like additional resources, please don't hesitate to reach out to the Centre for Safe Air webinar. The webinar is recorded and we'll distribute the links to the attendees. We look forward to seeing you at our next webinar. Thank you and goodbye, everyone.